Alright, so today we're going to be talking about something called the mean value theorem. And it's pretty important because it helps derive a lot of important applications. So the mean value theorem states that if f is continuous on every point on this closed interval of a comma b and differentiable on the open interval of a comma b, so it doesn't have to be differentiable on the edges, then there is at least one point C on, again, the open interval a comma b, where f prime of c is equal to f of b minus f of a divided by b minus a. So what does this mean? Notice how this right side of this equation is just us finding the average rate of change between a and b, right? Because f of b minus f of a, that's just like delta y, and then b minus a is just delta x, right? So it's just us finding a slope of a line between the points of the function defined by like what the function's value is at b and a, right? And we're saying that, so by this right side, we can call this like the average rate of change of the function in like between in that interval. And we're saying that there's some point inside the interval where the average rate of change of that whole interval is equal to the instantaneous rate of change, because that is what f prime of c is, right? So at some point our instantaneous rate of change is equal to rate of change is equal to the average rate of change. And to kind of like give intuition, let's say we have this like curve that kind of looks like this, right? And let's say this is point A, this is point B, right? We draw this little line between A and B. The slope of this line, so let's say the slope is m, that is the average rate of change of the function in this interval of a to b, right? And the mean value theorem is basically saying that given the function is continuous on every point between a and b and differentiable in that open interval, there's some point c, and like if we were to eyeball it, let's just say this is c. So there's some point c where if we were to find the derivative at that point, which is the instantaneous rate of change, the slope of that, or the derivative, is equal to m. So here f prime of c is equal to m. And that's basically what the mean value theorem is saying. And it's very important for us to have the fact that the f is continuous and differentiable on like these intervals, because imagine if we have something like the absolute value function, right? And if we were to find the average rate of change between this point B and this point A, we'd get this like horizontal line, and m is equal to 0. But as we know, if we were to try to find out any point between a and b where the derivative of this absolute value function is 0, we would not be able to find it, because firstly the derivative is undefined there, and then we have some constant negative value here and some constant positive value here, right? So plus and then negative over here. So here the mean value theorem doesn't fail because we're not accounting for cases like this. We say that the function must be differentiable in between, like in the entire interval of a to b, not including a and b. And here, at this point, the function is not differentiable because we have a corner, and so the mean value theorem doesn't apply in that case. But let's take a look at some cases where it actually does apply, and let's utilize the mean value theorem. So let's say we have f of x is equal to square root of 1 minus x squared. And we have point A is equal to negative 1, and point B is equal to 1. So so f of a, or f of b minus f of a divided by b minus a is simply, f of b is 0 because 1 minus 1 is 0, and similarly f of a is 0 divided by 2 is 0. And so now we have to find some point in between, in the interval of -1 to 1, where f prime of c is equal to 0. Right? And so how are we going to do that? So let's just find f prime of x. F prime of x is equal to square root of 1 minus x squared times 2 times -2x. And that simplifies to minus x and then over 1 minus x squared, right? And we have to query for when this is 0, and that's pretty clearly when x is equal to 0. And so here, c is equal to 0, and that's in between -1 and 1, and so we would expect this because this function satisfies this function on this interval satisfies all our constraints of the mean value theorem, because it's fully continuous between -1 and 1, and it's also fully differentiable in the open interval, because the only time where we're not differentiable is on x is equal to -1 and x is equal to 1, but we only need to be differentiable in between that interval, not the full case. So c equals 0 is our answer in that case. Now we have the mean value theorem, and by itself it doesn't really state much, but it has some very important properties that we can derive from it. Namely, one of the biggest things that we can get from it is the idea of increasing and decreasing functions. So that's the last thing I'm going to cover. So a function is increasing. F is increasing if for x1 less than x2, f of x1 is less than f of x2. And similarly, f is decreasing if x1 is less than x2 and f of x1 is greater than f of x2. And this, all it's saying is, basically, we have an increasing function if for greater values of x, our function itself is also producing a greater value. So like something like the linear function, right? That is an increasing on x, because this is x2, this is x1. x2 is clearly greater than x1, and our value is greater than x1 as well, right? And then, for example, f is decreasing. F is also, like, if f is decreasing, we have this case, right? x2, x1, right? And x1 is, like, the value at x1 is greater, but x1 is less than x2. And what's cool is we can use derivatives to find out when a function is increasing or decreasing. Specifically, if f prime is greater than 0, then f increases on a to b. Well, if f prime is greater than 0 on this interval a to b, and then if f prime is less than 0 on a comma b, then f decreases on a to b. And so we're saying that we can use the derivative of the function to find out where a function is increasing or decreasing. If the derivative is greater than 0 at some points, then at that point f is increasing. And similarly, where the derivative is less than 0 on some interval, then it's also decreasing on that interval. And the proof of that is actually very simple. Because let's say we have like 2 points, f of x2 minus f of x1. Well, we have f of x2 minus f of x1 divided by x2 minus x1, right? We're finding like the rate of change. And so if a function f is if some function f is like continuous on that interval and differentiable on the like closed interval, then we know that this is equal to f prime of c for some point at c, right? And so by taking x2 minus x1 to the other side, we can convert this into f of x2 minus f of x1 is equal to f prime of c times x2 minus x1, right? And so if f prime of c is greater than 0, right? If f prime of c is greater than 0, that must mean that, well, one thing that's for sure is that we know that x2 minus x1 is greater than 0 because by definition we're saying that x2 is greater than x1, right? So if f prime of c is greater than 0, then this term over here must be positive as well because the right hand side is positive since we're assuming f prime of c is greater than 0 and we know for sure that this is greater than 0. And that must mean that f of x2 is greater than f of x1. And so we're saying that if f prime of c is greater than 0, like we claimed here, then f is increasing. And we get this. Similarly, if f prime of c is less than 0, then this term on the left is less than 0 as well. And that means that when f of x2 is less than f of x1, we have decreasing. So we showed the relationship between f prime and whether a function is decreasing or increasing with this proof. And in summary, if f prime is greater than 0 on some interval, then f is increasing in that interval. And if f prime is less than 0 on that interval, then f is decreasing in that interval. And that has some very important implications on finding extreme values of functions, as we saw before. And that's one of like the biggest applications of the mean value theorem.